Welcome to your system design preparation session. Today we are diving deep into how WhatsApp handles 10 billion messages, and by the end of this lesson, you are going to walk away with complete clarity on this topic. So, let's get started. WhatsApp processes an absolutely staggering volume of data, handling over 10 billion messages every single day. To manage this, the system requires massive real-time concurrency. Millions of users must be able to send and receive messages at the exact same millisecond without the servers crashing. To achieve this flawless reliability, the engineering team built the core infrastructure using a programming language called Erlang, which is famous for its high availability. Furthermore, the architecture relies heavily on WebSockets to maintain persistent, two-way connections between your phone and the server. Finally, the entire system is wrapped in strict end-to-end encryption, ensuring that no one can read your private conversations. We will break all of this down step by step. Before we look at the technical architecture, I want you to truly visualize the scale of 10 billion messages. Imagine a massive, global network where data packets are flying across oceans in fractions of a second. If you were to process one message per second, it would take you over 300 years to process 10 billion of them. Yet, WhatsApp does this every single day, seamlessly. This level of scale completely breaks traditional web server architectures. You cannot simply use a standard database and a basic web server to handle this much traffic. The servers would instantly run out of memory, and the connections would drop. When you are designing a system at this magnitude, every single byte of memory and every CPU cycle matters. You have to rethink how servers talk to clients, how connections are held open, and how the underlying programming language manages concurrent tasks. This is the ultimate test of distributed systems engineering. Let's break down the high-level message flow when you hit send. It all starts with the sender client, which is the WhatsApp application running on your smartphone. When you type a message and press send, the app packages that data. This data is immediately pushed to the central chat server. The chat server acts as the massive traffic controller for the entire network, handling millions of incoming requests simultaneously. From there, the server routes the message into a highly efficient message queue. This queue determines exactly where the message needs to go next based on the recipient's status. If your friend is currently online, the queue instantly delivers the message directly to their receiver client, and their phone buzzes. But what if their phone is turned off or they have no internet? In that case, the queue routes the message into a temporary database. It stays safely stored there until they reconnect to the network. You might be wondering why WhatsApp didn't just use Java or C+ for their servers. Let's compare them. In traditional languages, concurrency is handled using heavy operating system threads. Erlang, however, uses extremely lightweight, isolated processes. This is crucial for memory. A standard Java thread might consume several megabytes of memory just to keep a connection open. An Erlang process uses only a few kilobytes. This means a single Erlang server can hold millions of connections open simultaneously, whereas a traditional server would crash from memory exhaustion. Next is fault tolerance. In a traditional app, an unhandled error can crash the entire server, disconnecting thousands of users. In Erlang, processes are completely isolated. If one process fails, only that specific user's connection drops, while the rest of the system runs perfectly. Finally, Erlang supports hot swapping. Engineers can push live code updates to the servers without ever restarting them, ensuring zero downtime for users. To truly understand Erlang's power, we need to look at its core design philosophy, the actor model. Let's write out the key principles. First, everything in Erlang is an actor. An actor is an independent entity with its own private state and memory. Think of it like a tiny, isolated computer inside the server. Second, we have message passing. Actors cannot directly access each other's data. Instead, they communicate exclusively by sending asynchronous messages to one another, much like sending an email. Because of this, There is absolutely no shared state. Since actors never share memory, we completely eliminate race conditions and the need for complex thread locks. This makes scaling across multiple CPU cores incredibly easy. Finally, the system uses supervisors. These are special actors whose only job is to monitor worker actors. If a worker actor crashes due to a bug, the supervisor instantly restarts it, making the system incredibly resilient. Let's pause for a quick knowledge check to ensure you are grasping these core architectural concepts. Here is your question. Why can an Erlang server handle millions of simultaneous user connections compared to traditional web servers? Option A says it uses a single, massive OS thread. Option B says it uses lightweight processes consuming minimal memory. Option C suggests it relies on heavy database sharding. And option D says it bypasses the CPU entirely. Take a moment and pick your answer. Think about the memory footprint we just discussed. The correct answer is B. Erlang uses incredibly lightweight processes that only consume a few kilobytes of memory each. This allows a single server machine to hold open millions of concurrent connections without running out of RAM, which is the secret to WhatsApp's massive scale. Now that we understand the server language, let's look at how your phone actually talks to that server. Historically, chat apps used something called HTTP polling. In polling, the client repeatedly asks the server, "Do you have new messages?" every few seconds. The server usually says no, wasting bandwidth and battery life. It is highly inefficient for real-time chat because of this constant, unnecessary overhead. To solve this, WhatsApp uses WebSockets. WebSockets provide a fundamentally different approach to client-server communication. Instead of constantly asking for updates, the client opens a single, persistent connection to the server when you open the app. This connection stays open in the background. Because the connection is persistent, the server can instantly push a new message down to your phone, the exact millisecond it arrives. There is no waiting, no polling, and very little battery drain. It is a true, two-way street. Let's look at a simplified code example of how a WebSocket connection is actually established on the client side. First, we create a new WebSocket object, passing in the secure WebSocket URL of our chat server. Notice the WS protocol, which stands for WebSocket Secure, ensuring the connection is encrypted. Next, we define an onOpen event listener. This block of code triggers the moment the persistent connection is successfully established with the server, letting us know we are ready to chat. The most critical part is the onMessage listener. Instead of us asking the server for data, this function sits quietly and waits. Whenever the server pushes a new message down the socket, this function automatically fires, allowing us to display the message on the screen instantly. Finally, when you type a reply, we simply use the send method on that exact same socket object to push your message back up to the server. While WebSockets are incredibly efficient for real-time chat, scaling them to billions of users introduces massive infrastructure challenges. First, every single open WebSocket connection requires a dedicated file descriptor on the server. Operating systems typically have strict, hard limits on how many file descriptors can be opened simultaneously. Engineers have to deeply tune the Linux kernel to allow millions of open files per machine. Furthermore, your load balancers have to be specifically configured to support long-lived connections, rather than the short-lived requests typical of standard web traffic. Another major issue is the thundering herd problem. If a server briefly goes down, millions of clients will attempt to reconnect at the exact same second, creating a massive traffic spike that can crash backup servers. Fortunately, Erlang's lightweight process architecture and fault-tolerant design perfectly mitigate these issues, allowing WhatsApp to maintain stable connections even during massive network fluctuations. Now that we understand how messages are transmitted, we have to talk about storage. How do you store billions of messages without crashing? The answer is database sharding. Imagine a massive load balancer at the front of your data center. When a message arrives, This system doesn't just dump it into one giant database. That would create a massive bottleneck. Instead, it uses a hashing algorithm on your user ID to determine exactly where your data belongs. For example, users with IDs starting with A through M might be routed to shard A. This is a completely independent database server that only handles a specific subset of the total traffic. Meanwhile, users with IDs N through Z are routed to shard B. By splitting the data horizontally across multiple servers, WhatsApp can scale infinitely. If traffic doubles, they simply add more shards. This ensures no single database is ever overwhelmed, keeping the entire system fast. Beyond speed and reliability, WhatsApp had to solve for absolute security. This brings us to end-to-end encryption. This technology ensures that a message is secured the moment it leaves the sender's device and can only be decrypted by the intended receiver. The most crucial aspect of this design is that WhatsApp's own servers cannot read the content of your messages. They merely act as a temporary post office, holding the encrypted package until it is delivered. To achieve this, WhatsApp integrated the Signal protocol, which is widely considered the gold standard for secure messaging. By encrypting data at the device level, the system effectively prevents man-in-the-middle attacks, where someone might try to intercept the data in transit. Ultimately, this architectural choice ensures absolute user privacy at an unprecedented global scale. Even if a server is compromised, the attackers would only find scrambled, unreadable data. This is a masterclass in secure system design. Let's break down exactly how this encryption works in plain English. It relies on a concept called public key cryptography. First, we have public key generation. When you install WhatsApp, your device automatically generates two mathematical keys. There is a public key that anyone can see, and a private key that never leaves your phone. Next comes the key exchange. When you want to message a friend, your phone requests their public key from the WhatsApp server. Think of this public key as an open padlock that belongs to your friend. The server hands you the open padlock. Finally, we have message encryption. Your phone writes the message, puts it in a box, and snaps your friend's public padlock shut. Once that box is locked, only your friend's private key can unlock it. Not even you can unlock it once it is sealed. This elegant mathematical process happens in milliseconds behind the scenes. Before we shift gears, let's test your understanding of system design at scale. Here is your question. How does WhatsApp ensure that no single database server becomes overwhelmed by billions of messages? Option A suggests they do this by disabling end-to-end encryption during peak hours to save processing power. Option B says they achieve this by using database sharding to split data horizontally across multiple servers. And option C claims they do it by routing all messages through a single, highly optimized Erlang node. Take a moment to think about the architecture we just discussed and pick your answer. The correct answer is B. As we covered earlier, database sharding is the critical technique used to distribute the massive data load. By hashing user IDs and splitting the traffic across many independent database servers, the system can scale horizontally and handle billions of requests without creating a single point of failure. Now that we understand the technical infrastructure required to deliver 10 billion messages, we need to ask a completely different question. What makes people actually want to send those messages? This brings us to our second major topic, the psychology of viral content and storytelling. Building a robust system is only half the battle. If you want to build a product, a video, or an app that reaches millions of people, you have to understand human psychology. Why do certain ideas spread like wildfire while others are completely ignored? It is not random luck. Virality is a deeply psychological phenomenon rooted in how our brains process information, seek novelty, and crave emotional connection. Over the next few minutes, we are going to deconstruct the anatomy of a viral hit. We will look at the specific psychological triggers that capture human attention, and more importantly, the structural storytelling techniques that refuse to let that attention go. The absolute foundation of any viral content is the hook. If you fail here, nothing else matters. A hook is designed to capture audience attention in the first 3 seconds. In a world of infinite scrolling, 3 seconds is all you get before someone swipes away. To be effective, a hook must disrupt normal scrolling patterns with novelty. You have to show or say something unexpected that breaks their trance. Immediately after breaking that trance, the hook must promise immediate value or entertainment. The viewer needs to realize that staying is worth their time. The most powerful way to do this is by creating a curiosity gap in the viewer's mind. You present a question or a bizarre situation that their brain desperately wants the answer to. Finally, the hook sets the emotional tone for the entire piece. Whether it is humor, shock, or inspiration, those first few seconds tell the audience exactly how they will feel. Once you have hooked the audience, how do you keep them watching? You use a storytelling technique called an open loop. The process begins when you introduce a mystery or a compelling question. This is the opening of the loop. Human brains hate unresolved patterns. When you open a loop, you create a psychological itch that the viewer feels compelled to scratch. But here is the secret. You must delay the resolution. Instead of answering the question immediately, you pivot to related context, build tension, or introduce a secondary storyline. This delay forces the audience to stay engaged because they are waiting for the answer. Finally, at the very end of your content, you provide the payoff. You close the loop by revealing the answer or resolving the tension. This delivers a hit of dopamine to the viewer's brain, leaving them satisfied and much more likely to share the content with others. Let's compare these two critical concepts side by side, so you understand exactly how they work together. First, look at their primary goals. The hook is entirely about grabbing immediate attention, whereas the open loop is designed to sustain long-term retention. They serve completely different functions. Next, consider the timing. The hook must happen in the first 3 to 5 seconds. It is a rapid strike. The open loop, however, spans the entire piece of content, acting as the structural spine of your story. The psychological triggers are also distinct. A hook relies on shock, novelty, or disruption to break a scrolling habit. An open loop relies on curiosity and the brain's deep desire for pattern completion. Finally, look at what happens if you fail. If your hook fails, the viewer scrolls past immediately. If your open loop fails, the viewer gets bored and abandons the content halfway through. You absolutely need both to succeed. Now that we understand the technical infrastructure that delivers billions of messages, let's shift gears to what actually makes those messages spread. We are diving into the psychology of viral content, starting with hook design. The first 3 seconds of any piece of content determine roughly 80% of your audience retention. If you lose them here, the rest of your video simply does not matter. To capture attention, you must use pattern interruption, which literally breaks the viewer's subconscious scrolling habit. You do this by creating a curiosity gap, introducing a scenario that creates an immediate, burning need for answers. But words are not enough. Your visual and auditory cues must align instantly to signal that this content is unique. Ultimately, strong hooks work because they promise a specific, high-value payoff to the viewer. You are making a psychological contract with your audience right at the start. Once you have hooked your audience, how do you keep them watching? The secret lies in a storytelling technique called the open loop. Let's break this down step by step. The foundation of an open loop is a psychological principle known as the Zeigarnik effect. By definition, this effect states that human beings remember uncompleted or interrupted tasks far better than completed ones. Our brains absolutely hate unresolved tension. In terms of practical application for your content, you must introduce a mystery or a core question early on, but deliberately delay the resolution until the very end. Think of it like opening a parenthesis and waiting to close it. The result of this technique is sustained viewer tension. Because their brain wants closure, they will keep watching, which leads to significantly higher completion rates. This is exactly how binge-worthy television shows keep you clicking next episode at 2 in the morning. Storytelling structure is important, but the fuel that drives virality is emotion. However, not all emotions are created equal when it comes to sharing. Let's look at how different emotional triggers perform. First, we have awe and wonder. This is a high arousal emotion with extremely high viral potential, particularly for shares. When people see something mind-blowing, they want their friends to experience it too. Next is anger or outrage. This is also a high arousal state, and it drives massive engagement, specifically in the comments section. It sparks debate, though it can be risky for brands. Then we have anxiety or fear. This high arousal emotion often leads to moderate virality, usually in the form of saves, as people want to keep the information to protect themselves later. Finally, consider sadness. Sadness is a low arousal emotion. While it might generate empathy, its viral potential is very low, usually just resulting in passive likes rather than active sharing. To truly master viral content, you must learn how to read audience retention curves. These graphs tell you exactly where your viewers are losing interest. Let's map out the 4 distinct phases of a typical video lifecycle. It always begins with the hook drop. In the first 3 seconds, you will inevitably lose a chunk of passive scrollers. Your goal here is simply to minimize that initial cliff by delivering a strong pattern interrupt. If they survive the hook, viewers enter the plateau. This is where your open loops and storytelling take over. A flat plateau means your pacing is perfect and the audience is engaged. However, most videos suffer from a midpoint dip. This happens when the script drags or when you repeat information. You must use visual changes to bridge this gap. Finally, we reach the payoff. If you deliver on your initial promise, retention holds steady, leading perfectly into your call to action. Let's pause for a quick knowledge check to make sure these psychological concepts are locking in. Here is your question. Which psychological principle explains why viewers keep watching to see the resolution of an open loop? Option A is the Pareto principle. Option B is the Zeigarnik effect. Option C is the Dunning-Kruger effect. And option D is the halo effect. Take a brief moment to think about what we just covered and lock in your answer. The correct answer is B, the Zeigarnik effect. Remember, this is the psychological phenomenon where the human brain remembers uncompleted or interrupted tasks far better than completed ones. By opening a loop and delaying the payoff, you create a sense of unresolved tension that forces the viewer's brain to crave closure. The other options refer to completely different concepts, like the 80-20 rule or cognitive biases. Mastering the Zeigarnik effect is your key to high retention. When you combine a perfect hook, an unresolved open loop, and a high arousal emotional trigger, you create something incredibly powerful. You are no longer just making a video, you are engineering a viral event. Imagine a piece of content as a digital spark. On its own, it might glow for a second and fade out. But when that spark is optimized for human psychology, it acts like a flare dropped into a sea of gasoline. The algorithm detects the high retention from your open loop. It sees the massive share velocity generated by the emotion of awe or anger. And suddenly, your content is pushed beyond your immediate followers, reaching nodes in the network you didn't even know existed. This is the true anatomy of virality. It is not luck, and it is not random chance. It is a calculated intersection of human psychology, storytelling structure, and algorithmic distribution working in perfect harmony to amplify your message globally. Before we wrap up, let's do a quick active recall exercise to cement these core storytelling concepts into your long-term memory. I will read a prompt, and I want you to fill in the blank. First one, the first 3 seconds of a video, which determine 80% of your retention, are known as the blank. What is the term? That is the hook. It is your pattern interrupt. Next, high arousal emotions like awe and anger drive high blank. Think about what people do when they feel these emotions. The answer is virality and shares. Low arousal emotions like sadness simply do not trigger the same sharing behavior. Finally, delaying a story's resolution to build tension creates an blank. What is this technique called? That is an open loop, powered by the Zeigarnik effect. If you can master these three elements, your content will perform exceptionally well across any platform. Let's bring all of this together. Throughout this lesson, we have explored the deep mechanics of digital communication. We have seen that virality is fundamentally engineered through human psychology, not just random luck. It starts with hooks that aggressively break patterns and create irresistible curiosity gaps. From there, you must use open loops to sustain viewer attention, ensuring they watch until the very end. We also learned that high arousal emotions, like awe and anger, are the absolute fuel for sharing and algorithmic growth. Finally, always let data and retention curves guide your ongoing content strategy. And that wraps up everything you need to know about system design and viral psychology for your course journey. In our next class, we will be moving on to advanced audience monetization strategies, so make sure you stay tuned. Finally, visit Examiverse AI Studio platform to automate your training modules and scale your educational content effortlessly.